Okay, good afternoon, everybody. I hope everybody had a good fall reading week. And we're all back. And just a couple of quick reminders. The first one is that assignment 4 is due by the end of Friday. But remember, the 8:30 rule is going to be in effect just like all the other previous assignments. So I'll accept your assignment up until 8:30 in the morning the next morning. So Saturday morning at 8:30. So just be aware of that. That deadline is looming up. And also, one other thing that I didn't write here is, remember, your second take-home test is also releasing on Friday. So I recommend, if you can, get the assignment done before you do your test. It'll help you prepare a little bit for it. As I promised, I did put out a format for this take-home test. It is on the course website. And I've also reopened up that little, like, for fun quiz if you find yourself really wanting to play around with the Canvas tool again. This time around, I'm allowing you to upload your own picture if you want to draw a picture. So if you're having issues with the Canvas, you can always upload a picture instead. But like I say in the description, it's at your own discretion because that takes extra time. When you're doing the actual final exam, you don't want to be using a lot of extra time for things like that. There won't be extra time provided. So just be aware of that. So that's just mostly there for accommodation reasons. I just wanted to make sure you have access to this if you need it. So other than that, course evaluations. You may have received an email about course evaluations for this course. I value your feedback considerably, both for the course and myself. So I really would appreciate if you complete this course evaluation, because this information is helpful for the department, both based on the course itself and what I'm doing for you here. So this stuff is really helpful to do. So please complete this course evaluation. You'll see it should be received by email to you, not on your courses. You complete it within the next couple of weeks. But like I said, this feedback is very important. And I take this stuff very seriously because for me as an educator, it's very important for me that I'm doing the best I can for students like you and everybody else. So, okay. So that being said, are we good to go to get started here? Give me 2 thumbs up if we're good to go. Okay, let's proceed. So we're going to be starting off with something that's going to first seem a little strange for me to bring up beginning of all these things, but you're going to see that this is going to ease itself into something we've been talking about previously. So I'm going to first start talking about a bit about set theory, strange enough. So I'm going to be talking about a notion called countability, and I'll be working up to a proof technique called diagonalization, or the diagonal method. Now, I'm not sure if you've ever seen this before. I'm not sure for the 310 students, if not, or so. If not, we'll definitely get accustomed to using this. So the first thing I want to do is we're harken back to some definitions from set theory. So the first I want to talk about what the cardinality of a set. So if I give you a set A, what the cardinality is. So often this is denoted with vertical bars, just like, remember when I denote the length of a string? If I want to say the cardinality of a set, I put the bars just like I did for a length of a string. All it is really just the number of elements in that set. So here's an example. So I have, say, 4 strings in here. I have A, B, C, cat, A, and epsilon. Remember, epsilon is the empty string. There's 4 strings in here, so the cardinality of A is 4. So far, this shouldn't be too bad. Now, I need to remind you of something that's a little bit important about counting. So you may or may not have seen this before, but you may be familiar with some of the terminology I'm going to use here. So we're going to need a definition that's going to help us determine if 2 sets are equal to one another in terms of their size, their cardinality. So if I give you 2 sets A and B, I need some way to do this. And a common counting trick is to establish what we call a correspondence or bijection. So that means that there is a function, we're going to call it f. It has to satisfy 2 properties. The first one is that it's so-called injective. Sometimes people call this one-to-one. That simply means that for every element in A and B, if I tell you that x is not equal to y, then most certainly for the function itself, f of x is not equal to f of y. So this is just to ensure I'm not having one element in one side of the function mapping to the same element on the opposing side. That's really the main reason why I have this. The other one is this so-called surjective or onto. So you may call it one-to-one and onto for a bijection, or injective and surjective. So the surjective property is simply that for all the elements in the B part, that there has to exist some element in A so that f of x is equal to y. Now you might ask, okay, well, Dan, why does this matter so much? Okay, so think about it like this. So if I have two sets, A and B, and I have a bunch of elements that are in A, and I have a bunch of elements in B. So what I would like to happen is to say that the two sets are equal to one another. I would like some way of pairing the elements from A with the elements in B. But if you think about this carefully, I'll let you think about this. But if you take this together, so first, this one ensures that if I give you some element x that's in A, it maps to some element in B. But we can guarantee that this isn't going to happen, where I have another element that's going to come along and map to the same element. That can't happen if the function is so-called injective, or one-to-one. Hence its name, one-to-one. For each element, there's going to be another element that I'm going to map to. They're not going to be two that are going to map to the same element in B. The surjective part, this is what ensures that everything that I have in B, there's going to be a matching element in A. There's going to be some element that's going to map to it. So when I take these two things together, what happens is I have some way of mapping each element in A to an element in B. So what does that mean? If you think about it and you think formally about the definition of a function, really what I'm doing is I'm pairing each element in A with an element in B. So when I say that there's a correspondence, what I'm really saying is that there's some way I can pair each element from A to B. And that's how I know that two sets are in fact equal in their size. They have the same cardinality. So is everybody okay with this up to this point? I just need to make sure everything's clear before we proceed. So are we all good with this? Are there any questions? Just don't be shy, because I'm going to start stacking things on top of this, which is going to get, it's like I said, it's going to get a little weird. So as long as you just understand that for each element in A, there's a corresponding element in B, so we can pair them. Yes? Yeah, so sure, the injective part. So all this is saying is that for every A, X, and Y, it must be the case that if I look at when X is not equal to Y, then most certainly it has to be that they're not equal when I apply the function. So that's what I was saying. So when I said this earlier, what I was saying is, okay, if I give you, say, something where X is equal to Y, so what I'm saying is, what happens is I'm just simply trying to say, if I have it where they're not equal on both sides, then most certainly they can't map to the same thing. That's what I'm generally just trying to say. So there might be a different way of writing this injective part here. Effectively, all it's saying is for each function, so my function guarantees that every one of those ones on the A, there's not going to be a way I have it where it lands on two values. And we often run into this, for example, when you have a function like a good example of one would be something like I think it's something like a parabola. So notice that whenever I look at this, notice that the function never repeats the same value twice when I put in x into f of x. So look, I'm looking at every x and every y. Okay. So another question, is the cardinality for real numbers open or closed interval means the same as other sets? So I haven't yet talked about the real numbers yet. Does that mean the same as the other sets? I'll clarify this in a little bit, because I will talk about the set of all real numbers shortly. But yeah, the whole idea is that, remember, what this is saying is that for every x and every y. So I just want to ensure that there's no way I can map something in x to the same thing that's in y. If they're not equal, then most certainly it can't be that they map to the same thing. But I do see exactly what little bit of confusion here. I'll probably go back to the notes and probably tidy this up a little bit to offer another example. But the main idea is I compare each A with each B. That's the big thing we want to take from this. Okay? So let's proceed as follows. So I'm going to define something we're going to refer to as countable. So this is going to be an important concept that's going to be littered throughout this lecture and possibly the next one at minimum. So here's the idea. Suppose I give you some set A. I want to know whether it has a certain size. In particular, I want to make sure that it's at least the same size as the set of all positive integers. You might think of this as the natural numbers, depending on your definition of the natural numbers. So I'm going to define the following. So I'm going to say that if A is finite or it has the same cardinality as the set of positive integers, then we're going to say it's countable. If you want to describe the set A as an infinite set, you would describe this as a countably infinite set. But that all falls underneath this definition of countable. So I want to give you some examples of countable sets. So I'm going to start off with something that, remember, if you've never seen this before, I might blow your mind a little bit. But if not, that's okay too. For some of you to be like, yeah, no, Dan's just having a little fun here with infinity, which is what's happening here for the most part. So suppose I consider the set of all even positive integers. So this means I'm considering 2, 4, 6, 8, 10, and so on. So this is the list of all the even positive integers. Now you might ask, is this set countable? So under this definition, it's either going to be finite. This is most certainly not finite. So we have to use the other condition. We have to ask if it has the same cardinality as the set of positive integers. So now this is where it gets really weird. Like I'm telling you, like this is gonna blow your mind. I know when I first seen it years ago, I was like, wow, that's so strange. So remember my definition of cardinality and what I said means for two sets to be, in fact, of equal cardinality. So it means that there has to exist some function where I can pair each element in one set with an element in the other set. So I'm going to form a correspondence between the two. So watch this, watch this. This is where it gets a little weird. So I'm going to use a function, f of n is equal to 2n, like this. So what I'm going to do is for each one of the positive integers, I feed this to this function, and then I see what it spits out for me. So if I give a 1, it outputs 2, right? Because it's 2 times 1. If I give it a 2, it gives me 4. If I give it 3, it outputs 6. 4, it's 8. 5 is 10, and so on. This is where it gets really strange. Like I said, you would think that they shouldn't have the same size because I've eliminated half of the numbers, right? Because I've knocked out 1, 3, 5, 7, and so on. all the odd positive integers. But this is the weird part. They actually have the exact same cardinality by the definition of my bijection, because this is a bijection right here. So notice that for every one of the positive integers, I'm able to map it to a positive even integer. It is very weird, like I said. When I first seen this, it's like, that's really strange. So this is what I'm trying to say. This is going to get really weird. So weird the dogs are going crazy. It's blasphemy to them. So let me see here. So we have all the even positive integers. Those are all going to have the same cardinality as the set of positive integers. But here's the weird part. Remember, positive integers, the set of all positive integers, this is in fact an infinite set, right? So I've established that this infinite set has the same size as the set of all positive integers. So now we have some way of talking about some other set that's also infinite but has the exact same size, which is very strange. Okay, now here we're going to go even further. So suppose I have this set of all integers. The set of all integers. So you might say, Dan, the set of all integers includes 0 and the negative numbers. That most certainly can't have the same size. So this is so notice here that I used a function to map each positive integer to an even positive integer. But yeah, so there's going to be a very strange concept where we're going to have where we can compare, or we can say that two sets that are of infinite size actually have the same equal infinite size. We're going to have a more careful notion of this in a little bit. So if I have the integers, believe it or not, I can do this. So we can use a function that looks like this. F of n is going to have two cases. It's a piecewise function. It's going to be n over 2 if n is even. And it's going to be 1 minus n over 2 if n is odd. Now this is where it gets really weird, because remember, all I need is the existence of one of these bijections or correspondence. If I have that, we're okay. So you might ask, Dan, what does this even look like? So suppose I have the set of all of my integers. So I have 1, 2, 3, 4 like this, -1, -2, -3, -4 like this. You might ask, what does this look like? Which is kind of strange. So if I put in a 1 into this function over here, notice that 1 is in fact odd. So it's going to be 1 minus 1 over 2, which is just 0, right? So notice that this right here is just going to, so this is right now just going to be 1. And then if I have 2, well, 2 over 2 is 1. So I have 2. Now this is where, watch how this is going to play out. This is kind of weird. So when I get 3, I'm going to have -2 over 2, which is just 1, 3. And then if I put in, say 4, well, it's 4 over 2, which is just right there. And you can keep doing this over and over again. So essentially the way it's going to work out is it's just going to be like this. 3, 4, 5, 6, 7, 8, 9, and so on. It's going to swing back and forth like this. So you can establish that the set of all integers is also countable. Yes, and it sounds very strange, right? This stuff blew the minds of mathematicians like in the 1900s. It was the late 1800s to be more precise. Like it blew the mind of a lot of mathematicians, and they're like, how dare you talk about infinities like this? It's just kind of weird. A lot of this came out of the formulation of set theory when mathematicians like Georg Cantor was first really presenting some of these versions of set theory. So now you have this notion where I can just have the set of positive integers, its size is equal to this, and its size is also equal to this. So you might ask, what else can I do? So I'm not going to go into the details here just for the sake of time, but you can even go up to the rationals, for example. So that's the set of all rationals. So these are all your fractional values, like 1/2, 1/4, anything that is a ratio of two integers. The way it works is that you build a table and you write the fractions out in a fashion that looks sort of like this. If you want more of the details, I give a page link if you're curious about this in the Sipser book, if you're curious about it. If not, there's a lot of resources on how to get that one. I'm not going to worry so much about that. It's mostly about the idea of what countable set is. So you can do it for the rationals as well. One that's going to be more relevant for us I want to talk about is actually sigma star. You might ask, Dan, why would I talk about sigma star? It's because it's going to be very relevant for what we're going to talk about. Because I started talking about all these sets of numbers and stuff. What I would like to do is I would like to have some way of talking about strings that are represented by strings that belong to sigma star as numbers. That's where we're going to go in this with the long term. It's going to be kind of strange. But keep following carefully with me. Okay. So another countable set is sigma star for any fixed alphabet. For any alphabet. Any alphabet sigma. So this is another example. Some ideas I'm going to describe here are going to be relevant for us later. So I'm going to first describe to you the set theoretic way you would actually do this. And then I'm going to describe a very specific, narrower way we're going to use it. Okay? So watch this. So remember the definition of sigma star. Remember, it's the strings of all of length 0, union all of the strings of length 1 over that alphabet, length 2, length 3, length 4, and so on. This definition actually matches quite nicely how you'd actually enumerate this in a set theoretic way. So there are only a finite number of strings of each length So one may list all strings of length 0, then length 1, then length 2, and so on. Now, when I have something like this, and remember back the definition of what sigma star is, this all has a natural correspondence to me performing unions on finite sets. So I have a finite set, union another finite set, then union another finite set. Now, the number of unions that actually happens with our definition of sigma star is actually accountably many of them. So when I say that, I mean that the number of unions is actually countable. So it's kind of strange. So I'm just going to state this as a fact. If you're curious about this, I can always try to point you in the right direction. A known fact, so I'm just going to state this as a fact because this is not really where I'm focusing so much. A known fact is that countably many unions of finite sets is countable. And if you're wondering where this comes from, it actually comes from that you can map this to, if I took the Cartesian product of two sets of integers. So if you're wondering how you would go, like how this even comes about, is that you show that the Cartesian product of this, so this result right here, you'd show that this is countable. If you write out the definition of sigma star, and then what you do is you try to directly map each set that you get out of one of those as a pairing within this, along with a couple of interesting other facts. You can actually prove this set theoretically. But I'm not going to be focused so much on this. Just know that this is a countable set. That's the thing you need to be aware of. So just remember that sigma star is a countable set. But I want to show you another idea. If, say, for example, you have, so this is different from this. So if, say, the alphabet was binary, like this, I'm going to show you an interesting but much simpler way of drawing on the correspondence between the integers and my sigma star. So this is a trick that we're going to use a little later on. I just want to show you up front so you can see, hey, look, that's actually kind of nice. Just because it's relevant. Note that this argument also will work for any alphabet with two symbols, and you can also generalize it for any alphabet. But it's not going to be as clean as in this case. You have to rely on a different fact about countable sets to make it work more generally. In that case, it's actually just that any subset of a countable set is also countable. The proof basically goes that you go down the list and you start crossing out things. But I'm not going to go into those details here. This one will work nice and clean for us. So if we know that the alphabet is, in fact, the binary alphabet, there's a much simpler argument. There is a much simpler argument. And this is the one that's going to be relevant mostly for us. Is what I do. So one can encode. For binary, it's straightforward, but I'm just writing this for the sake of generality. One can encode each symbol of sigma in binary and prepend, that means put at the beginning of the string, 1 at the beginning. And enumerate them in standard fashion. So what I mean by in standard fashion, I mean in increasing binary value. So lexicographic, but also increasing. So you start with the shorter strings, you work to the longer strings, list them by their numeric value, smallest to largest. Then enumerate them in standard fashion. That's my hand wavy way of describing that, is standard fashion. Standard fashion. To obtain a unique integer for each string of sigma star. So there's going to be a correspondence. I'm going to show you, just for the sake of simplicity, I'm going to use the following example. Just because I feel like it gets the idea across. So suppose I want to have not 1, and I'm going to write the base of the number just to make this a little easier for you to see. So this is number 1 in base 10. So this is our first number in the set of positive integers. What I'm going to do is I would like to pair this up with epsilon. So I would like epsilon to correspond to 1 and work my way up that way. So if you notice the way I've described this, if I give you a string W like this, What I'm telling you is put a 1 in front of it. That's all I'm saying to do. So here, since the string has no symbols, I just write this as 1 base 2. So that's just me saying base 2. So what I'm saying is that epsilon is going to correspond with 1 using this trick. And then if I do 2, so if I have 2, all I'm going to do is I'm going to correspond this with... Now, for simplicity, just to illustrate this point, I'm going to make it so that 0 is A and 1 is B, just to make it a little bit clearer what I'm up to here. Like I said, it works for any alphabet with 2 symbols. So suppose I give you the string A. So just, I'm going to assume A is encoded with 0 and B is encoded with 1. So remember, all I say is you start off with the 1 and then you append whatever that symbol is encoded as. But what's 1, 0 in binary? It's 2, right? You can keep doing this. So if I give you B, this is 1, 1, because I start with a 1 and then I give the encoding of B, which is just 1. But what's this? This is 3. 3 in base 10. You can keep doing this. For example, if I give you, say, AA. AA, this is no different than me writing, remember the leading 1. Then I have 2 zeros, each represents an A. So 2 A's. But what's this? This is just 4, right? And you can keep this process going on and on and on. For someone like you, is this a little bit more transparent of why you can argue, say, the binary alphabet is countable? Can you see why? Yeah, see, this is a lot clearer. I like this explanation a little bit more. But yeah, you can generalize this to any alphabet, but you have to deal with logarithmic numbers of bits, and then they're not going to necessarily map perfectly to all of your positions like this. You're going to have to do some, what they call, and when you're enumerating sets like these, you're going to start having to crop out enumerations of the list where you have gaps, which cause you to have to shift things. It's easier to invoke a property like this if you're going to do something like that. But yeah, so just know that sigma star is countable. That's the big thing I want you to take from this. This is going to be the fact we're going to need. Now, this alludes to where we were earlier, where somebody was asking about, okay, well, we talked about sizes of infinite sets being equal, which is very strange. It's a very strange thing. So what does it mean then when I present you a set where they don't actually have the same size? Do those even exist? And the answer, unfortunately, is yes, they actually do exist. And they create a whole bunch of weird things in mathematics. Like, I mean strange stuff, like really weird things that I'm not even going to be able to talk about in this course because there's just so many of them. So when mathematicians first realized that, hey, look, there's actually different sizes of infinities, this kind of really threw the carpet underneath a lot of mathematicians because they really like the idea of infinity being this one very specific thing. But when you think about it from a set theoretic standpoint, it really changes the whole game. Yes, somebody pointed out something I'm going to talk about in a moment. So we're going to define something called uncountable. You might know this as uncountably infinite. So this is just simply a set A that has no correspondence. Has no correspondence with the set of positive integers. And here's the weird part, is that people use these kind of sets all the time in mathematics, and it's very interesting that it's just like people just sort of use it just like as a given, which is it's kind of weird from a weird... I don't necessarily think it's weird to use them. They're more very practical things to have. But it's very strange from, say, somebody that was coming more from a background that... Say, for example, when we talk about our machines, we always have an exact description of those machines, and they always have an exact way I can construct them. Now, for some sets of numbers, you do have things like that, but they have all sorts of very strange consequences as a result if you do this. One example of such a thing is the set of all real numbers. So a good example of an uncountable set is the set of all real numbers. And you might ask, Dan, can you talk about those details? Unfortunately, not so much at this stage. And in fact, some of the things they're far more appropriate to be talked about in a real analysis class, which this is not that. So set of all real numbers, you might know this as the blackboard R. That dreaded blackboard R. And this is actually even true when you include, so this is including when only considering all real numbers between 0 and 1. Weird, right? It's very strange. The argument that we use to do this is called diagonalization. I'm going to be showing you how this works. Yeah, we'll have time today. Excellent. So I'll just mention that this is proven using something called diagonalization, which I'm going to show you how the trick works. Sorry, I was getting a little ahead of myself. Diagonalization. Or sometimes people call it the diagonal argument or Cantor's diagonal argument. So I'm not going to focus much on the proof of this, but it most certainly is one of the weirder of these sets. It has all sorts of weird things that mathematicians will bicker all about, and sometimes even computer scientists get into the weirdness with. For example, believe it or not, like this set consists mostly of numbers you're never going to be able to compute with a Turing machine, which is very strange. That's why I said it's strange. It's a very strange set. If we have time, I might be able to convince you of that fact, depending on how much time we have and what we can cover. But if you're curious about that, bug me. I might be able to point you in the right place to look at that. Another one, this is one that's very fundamental. It's called the power set. We've used the power set before. So the power set, so if I give you a set A, and I assume, for example, that it is a countable set. So any countable set, it includes infinite sets. The power set of A is actually uncountable. Now, this is the kind of fundamental aspect of this. If you're wondering why this is true, this is actually a way you can cast the following theorem. It's by Cantor, the one I mentioned earlier. So this comes from a theorem called Cantor's theorem. A way you can phrase this is that the cardinality of A is always less than the cardinality of the power set of A. And this is true for all sets A. So this is true for any set, finite or infinite. Now this is the weird part. Now to get this really weird thing off my back. Okay, if you're wondering, there's a weird thing about this result. First, notice that if I take the power set of A, the power set of A is indeed greater than, in terms of its cardinality, to A, right? Well, what happens if you take the power set of the power set of A? Is that infinite? Is that infinity larger than the one just for the power set of A? So so what I'm saying is, so if we know that A is in fact less than the power set of A in terms of its cardinality. So what if you do the power set of the power set of A? So suppose I do the power set of the power set of A. Any ideas of how this would relate with the size of the power set of A? And I remember, I said this is true for all sets, not just countable ones. It's the same rule. So this is going to be very strange to somebody like... So I can keep repeatedly applying the power set to this, and I can keep making larger and larger infinities. So big that you can never imagine them. And there's special names that different cardinalities of infinities actually have. Just as an example, this isn't really relevant for this course, but I feel like I want to mention it seeing as I'm right here at this stage. It's known that the cardinality of the power set of A is in fact equivalent to the cardinality of the set of all reals. So I could have easily placed the set of all real numbers right here in my chain of inequalities. And a fundamental question in mathematics that people have lost their mind over is there any set with a cardinality between these two? That's a very fundamental mathematical question. And you might know this as something called the continuum hypothesis. This is, does there exist one that sits in between? If the answer is no, then most certainly every set that you're going to know is either going to sit on one side of this, or on this side of this, or go further on that way. And this is like a fundamental mathematical question. But we're not really, believe it or not, we're actually not here for this. What we're here for is to talk actually about how we can use a lot of the mathematics that we use to derive some results like this one. Because the same technique that Cantor used to blow a hole through modern mathematics, I mean, like, not literally, like he didn't go in there with a bazooka. Just don't try to imagine this, okay? He went in figuratively with a bazooka, annihilating the concept of having a formality in mathematics where we have only one infinity. There's infinitely many possible infinities. There's so many of them that I can't even imagine them. Okay, so does everybody get the general gist? So there's these countable sets and there's uncountable sets. Apologize for that being a random little louder there. But yeah, so there's these two types of sets that we're going to be interested in. I'm going to do an example of this so-called diagonalization. So this is where it's going to get a little bit... You thought this was going to get weird. It's going to get even stranger. And I assure you that by the end of next lecture, you'll be asking yourself, what the heck is going on? For some of you, this might be the first time you've seen some of these ideas, and I encourage you to think about them or ask me questions. These are somewhat, they're very strange. I know when I first learned this stuff, it kind of blew my mind. I'm like, it's like, how is that possible? So I'm going to show you how you can prove a set is uncountable. So what I'm going to do, and this is the game plan. So when you're trying to do this, a common technique is this diagonalization. And here's how the argument goes. You assume that there exists a bijection between the set of positive integers and your set of interest, the one that you want to show is uncountable for the sake of a contradiction. Then what you do is, under the assumption that there is a bijection, that means you can list all those elements. So what we're going to do is we're going to show that there is no way you can map, there is no correspondence between the set of positive integers and the set of your interest, which is going to get a little bit weird. It is a little weird. So here's the theorem I'm going to prove for you. The set B of all infinite binary sequences, you can replace this with strings if you'd like, is uncountable. So here's how it's going to go down. So remember, like I said, the game plan is I'm just going to use contradiction. So I'm going to start off by assuming, B is countable. So by the definition of countable, that means that there exists that bijection or correspondence, whatever terminology you'd prefer using. Then there exists a bijection. A bijection that's going to take, I'm going to call it F. It's going to take each positive integer. It's going to give me one of these infinite binary sequences. Since B is not finite, that means that there's going to be some infinite sequence for which I can list you all of these binary sequences in B. There is an infinite sequence. An infinite sequence of binary sequences. That's a lot of sequences. Binary sequences. I'm going to call them B1, B2, and so on. That lists every binary sequence of B at least once. Of B at least once. So let me just wrap this sucker up. So let's see here. So what I'm going to do is I'm going to list each one of them out. So I have B1, B2, B3, B4, and so on. And I'm going to list it like this. B11, B12, B13, B14, and so on. I'm going to have B21, B21, B22, B23, B24, and so on. So I'm just you almost look at this sort of like a matrix. That intuition isn't that bad either to use. B31, B32, B33, B34, and so on. Remember, these are infinite binary sequences. They're not finite. B41, B42, B43, B44, and so on. Okay. So there exists some correspondence. Remember, I don't know what these are. I'm just giving them names. And I'm telling you that there's a correspondence between that and the positive integers. So just like I did earlier, there has to be existing some function such that there's a correspondence between the set of positive integers and all of these binary sequences. So indeed, under the assumption that B is countable, this lists every single possible binary sequence. So here's an interesting idea. What I'm going to do is I'm going to construct another binary sequence. So I'm going to construct another binary sequence. And I'm just going to call it X. It's going to be X1, X2, X3, X4, and so on. So it's another infinite binary sequence where for all I greater or equal to 1, I'm going to define it like this. So I'm going to say xi is going to be 1 if bii is equal to 0. So if I look in the ith position of the ith binary sequence, if I see a 0, I'm going to flip the bit to be a 1. Same idea here. If I have a 0, if I see then the ith binary sequence in its ith position, I see a 1, I'm going to set this number, this xi, to 0. So I'm going to construct a new binary sequence. Now, under the assumptions that I have here, this sequence x should be in this list, right? Because it's countable, right? Well, this is where it gets weird. So for every I greater or equal to 1, x is not equal to bi, as xi is not equal to BII by construction. So let me just show you what I mean by this. And this is where the name of this technique comes from. So I look in the first position. So remember, I construct x1 based on this position. If that's a 1, I set it to be x1 being a 0. So I look at my sequence of x1 against b1. Sorry, yeah, b1 here. Notice they aren't equal because the first position mismatches, right? By definition. Now, I look at the second one. Remember, I flipped the bit in this position. They mismatch. So that means that it does not equal this sequence, nor does it equal this one, because the first position mismatched, the second position mismatched. Same idea here, same idea here. Notice that you have down the diagonal. So this is why we call it the diagonalization or diagonal method, is notice I've built you a new sequence that is none of the elements in my list. It's none of them. So whichever one you give me, I can show you that x is not equal to it. But what does that mean? Can somebody tell me? On that last thing, we will wrap this up. It's not countable, right? Because I just showed you that there is one element that is not put into correspondence with the positive integers. Exactly. However, x is in B, but it is not in the above list. Now, the big important thing you need to notice here is that I made no assumptions about what f is. All I said is it has some correspondence. That's an important fact in this argument, which is a contradiction. And we're done. Therefore, the set of all infinite binary sequences is uncountable. So isn't this a very strange argument, but it's a very clever one. So all I did was I assumed I could list them all and pair them up with an integer. And then all I did was I constructed a new sequence that cannot by construction be anywhere in this list. And by doing that, I've shown you that there is an element that isn't in the list, hence there is no bijection because my argument doesn't really depend on what f specifically is. We're going to see next time, I'm going to show you how you can turn Turing machines into numbers. And then we're going to see if there exist languages that no Turing machine can capture, as in it can recognize. So with that being said, I want to say thank you very much and have yourself a beautiful day. I'll see you later.